Good afternoon, all. Geotech Asia 2025 warmly welcomes you for today's theme session titled Slope Stability and Landslides. Before moving further, I introduce myself. My name is J. Naveen Kumar, a research scholar at IIT Bombay, and session coordinator for current theme. Now, I would like to introduce the chair for the session, Dr. Sri Valsa Kotalyar, to occupy the chair on the stage. And co-chair, Engineer AVS Chakravarti, please, sir, occupy the chair. The chair for the theme session, Dr. Srivalsa Kolatiyar, is Associate Professor in the Department of Civil Engineering at the National Institute of Technology, Karnataka. He pursued MTech from IIT Kanpur, PhD from Indian Institute of Science, and served as international research staff at UPC Barcelona Tech, Spain. With over 15 years of experience in teaching, research, and consultancy, he is passionate about advancing the knowledge and practice of civil engineering, especially in the areas of seismic hazards, landslides, reinforced earth, pavement geotechnics, landslide mitigation, and disaster risk reduction. The co-chair for the session, Engineer AVS Chakravarti, graduated with Master of Technology in Geotechnical Engineering from NIT Warangal. Currently, he is serving as Chief Engineer at Cochin Engineering and Consultancy Services Private Limited. Chakravarti is a life member of Indian Geotechnical Society New Delhi and Secretary of Kochi chapter. I sincerely welcome and heartful vote of thanks for Dr. Srivalsa Kolatiyar and Engineer AVS Chakravarti for accepting as a chairman and co-chairman for the today's theme session. To the chairman, I officially inform that we have 5 presentations are available as of now. I request the chair and co-chair to permit the session coordinator to start the session for presentations officially. Permitted. With official permission and due respect, now I, the session coordinator, officially hand over the session to chair and co-chair to lead the session.
Good evening, everyone. Rather, good afternoon. Hope we have been having good sessions all the 4 days. We are on the 4th day, second half now, and we are progressing towards the concluding ceremony this evening. There's too much of a technical takeaway from all the sessions we had. Let it be the plenary invited sessions or the parallel sessions. So this session, today afternoon, we are going to have on the theme slope stability and landslides. I have my chair, Dr. Srivalsa Kolatiyar. We have 8 papers in total for this particular session to be presented, of which, as they were mentioning, about 5 others are already there to present their papers. We hope the others also may join. And the theme speaker is Engineer Taro Hiromana, who will also be joining anytime now, and then we'll have the theme lecture in between. So I hand over the mic to Chair Srivalsa Kolatiyar, Doctor.
Thank you, sir. So it's a pleasure to be here along with the Engineer AVS Chakravarti. So the slope stability and landslides, it is a very important theme, especially we are sitting very close to the Western Ghats, where we experience multiple landslides every year during monsoon. So as theme speaker is yet to arrive, we will start with the contributory presentations. So the first presentation is by Aditya Tarafdar on application of GIS-based logistic regression for landslide susceptibility mapping in Gajapati district, Odisha, a case study. You can take about 8 minutes, 8 to 9 minutes.
A very good afternoon to everyone present here, respected chair, co-chair sir, and all my dear colleagues here. So my presentation is about landslide susceptibility analysis in Gajapati district of Orissa. So my work is mostly related to the use of GIS in landslide mapping. So I'll start with, so these are the contents of my slide. I'll go from the introduction till the conclusion here. So why now landslide susceptibility? So landslide, as we all know, so I wouldn't be explaining about landslide here. I have all the experts around me. So what our paper deals with is, we are using GIS to calculate the locations where landslide susceptibility is there. We are just going to prepare a landslide susceptibility map for Gajapati district of Orissa. Now why this district? This district falls in the Eastern Ghats. So it's just in the beginning of the Eastern Ghats. It has good slope, rugged terrain. So it's a very good study area for doing this. And one more thing, there's very less papers on this area. So due to that, like there is very less number of landslide mapping here. So we took this area for our analysis. Now we had taken 7 conditioning factors. What these conditioning factors are there and how they are used, I'll be showing in the coming slides. So this is the study area that we are taking here. So it's in the eastern part of Orissa. We have, so the rainfall here is moderate rainfall we are having here. The main thing here is the terrain. So the terrain is what results in the landslides in this area. So I'll just go into the, so this is the area here. So now we had taken those 7 conditioning factors. Among this, we had taken topographic conditioning factors like slope, aspect, curvature. Some hydrological factors, hydrogeological factors were taken around, like from the distance from rivers. So these are the factors that were mostly affecting the study. We had taken many more factors for analysis, but we had seen those values were not, they were not giving sufficient values or sufficient changes in the results. So these are the 7 factors that were most responsible for the landslide susceptibility here. So these are the 7 conditioning factors. Slope is related to the steepness, aspect is to the orientation of the slopes, curvature, whether it is concave, convex, like that. We have TWY, that gives the moisture content of the soil at some places. We have LULC, very important in GIS statistics, distance from river, distance from slope here. So this is the slope factor. The interesting part is most of the district covers around moderate slope here. So we are getting a moderate slope of more than 15%. These are the regions that we were expecting to be mostly susceptible to our landslide analysis. So after that, we had our aspect factor. So aspect is the curvature, the direction of the slope. So here, if the slope is directed towards north, we have north curvature, we have towards northeast. So all the 8 directions were taken into account here. After that, we have the curvature. Curvature, why so important? Like if it is concavely curved, so it has the tendency to attract runoff there, to make the runoff stay, increase the pore pressure, result in more landslide. If it is convex, on the other hand, it has the tendency to drain the water from there. Flat area just comes behind that. So we have curvature, we had TWI. TWI is related to the water, how much a given area can store water, which are the areas that have more moisture content. So TWI is a function of the slope here, so mostly it is related to the slope. From the slope map, this was calculated out. Then we had the distance from river. The closer the slope is to the river, the greater the tendency for landslide. In many studies it was shown. So we had taken the distance from river and distributed it accordingly. Then was the distance from road. Distance from road and LULC were the anthropogenic factors here. So distance from road, the closer the slope is to the road, the more disturbance it has taken into account. The greater the disturbance, the more the probability of the landslide. That is why this factor was taken and it was divided into different distances here. We had divided it into 6 classes here. Then we had the LULC factor. LULC is the land use and land cover factor. So we had divided this study area into different land classes. All these classes were taken from the S3. S3 does this land use, land cover categorization every year. So we had taken this data from them. So after taking all these factors, we took all these factors into ArcGIS. did the resolution classification. All the resolutions were made into 30-meter resolution. That is that is directly related to the DEM here. So after that, once we got the input from ArcGIS, we had used bivariate statistical analysis using logistical regression. Why bivariate? Because my one factor was whether landslide can happen or not happen. So this was my dependent factor. My independent factors were aspect was independent factor, say LULC, these were my independent factors. So pixel by pixel, we had done this analysis, and at every pixel, which of those 7 factors gave us the most relevant data, that was taken into account. So this is the equation for logistical regression here. So here, that Px is the probability factor that is taken here. If Px value is less than 0.05, that given factor, that given for which this is curving, that is taken into more. Now here the beta values are for, now beta and x. So beta values are the regression coefficients that is taken from that is the output of logistic regression. My x1 and x2 is the pixel values for each of those factors. So I had 7 factors, so x used to run from 1 till 7. So here LULC was found to be the most important factor in this our analysis. So from here, this was the final landslide susceptibility map. That was our output. So what we had done, we took the inputs from ArcGIS, all those 7 factors. Then we incorporated in RStudio to do the logistical regression analysis. Then the output was again taken out from ArcGIS, and this is the susceptibility map. In this susceptibility map, the areas that are in green, those are having low probability of having a landslide. As we go towards red, the probability of landslide becomes more and more. So those areas in red are those areas in this district that has the most probability of having a landslide anytime soon. Now from here, out of those 7 factors, 2 factors were the most significant here. One was LULC. So what we had seen was that LULC was giving the most greater value of P there. So it was coming less than 0.05. For the other factors, the P factor was coming more than 0.05 here. For example, we were getting for the other factors, distance from river slightly more than 0.05, almost significant. So these were the 2 factors that is like from our study controlling the susceptibility of landslide in this district. The other factors, slope, aspect, curvature, they weren't giving that relevant results. So the interpretation or the final conclusion, what I can say is that from our study, 2 factors in Orissa, one is land use landslide and the other is distance from river, were the most contributing factors in this analysis. The other factors, although significant, but they weren't producing that amount of disturbance into that area. So these were and the landslide susceptibility area, we had seen that very less % of the area. I'll just go back to show you. I think it's not going. Okay, so yeah, so only 2.3% area was highly susceptible. Other than that was moderate and very low susceptibility.
You can take 1 more minute, okay?
Okay, sir. So with this, I'll just come to the conclusion. So like susceptibility maps are used by the different departments for their planning purposes. So if I want to do a road construction, so which area is more more suitable and all, that might be used. So with this, I'll just try to conclude my study. So these are the references. I would like to thank my co-authors here who had worked, Dr. Ruby Chakrabarti, our assistant professor from our department, and Soumyaranjan Satapathy, my co-author here. So I would like to thank Geotech Asia for giving me this podium here to present my study. With this, I'd like to thank you, everyone.
Yeah, very good presentation. We can have a couple of questions if there are any questions from the audience. Yeah, please, go ahead.
So, Nice presentation, good clean slides.
Thank you.
So, from all this, what would you say? Which factor you think is more important to pay attention to?
Like if we are doing the study for this district area, so like the slope and those other factors, they weren't giving that amount of result. The most important factor here was LULC. Why LULC? Because LULC gives us the disturbances that we are doing to the environment. So LULC, if it is a built-up area, so a built-up area has a lot of disturbance there. So for this study, like I'll show, we had done the same study for East Khasi Hills district of Meghalaya. There the most important factor was slope. So, but in this, so it differs from area to area, from region to region. So there are many other methods, numerical methods to take out like which factors give more disturbances and all. But like it differs from area to area. For this area, if you are doing the study for Orissa, I'll say LULC is the must factor here.
So, when 2.31 you had mentioned is
Yeah.
more susceptible to that percentage. So, for all those areas, your LULC only was the key factor.
Yeah, no, like the key factor was LULC, but that 2.31 that we got, that was a combination of all, like what happened, na? Like in logistic regression, we had taken the beta values, we had taken the p values. So from there we got which factor are like most relevant or like they are mostly like affecting the landslides. And like that 2.31%, that was a combination or collection of all those factors. Like when we used all those factors in that equation, so that final p values that we were getting, so for 2.3% was the combination of that all. So we cannot just say just due to LULC there.
Thank you.
Thank you.
Thank you, Mr. Aditya Tarafdar, for the presentation. You are very much in time of 8 minutes also. So we'll have the second presentation on the topic Modeling of Lay Boys de Lava Glaive 2021's Landslide at Switzerland. This being presented by the author J. Torch.
Ladies and gentlemen, good afternoon. Today I would like to talk about the modeling of a Bois de la Glaive 2021's landslide in Switzerland. I'd like to start this presentation with a short introduction, then the methodology employed, an historical review, parameters of a landslide, modeling, discussion, and finally a conclusion. Switzerland is a small country densely built up with steep topography. 6 to 8% of the territory is at risk of landslide. Between 1972 to 2022, landslide and rockfalls damages count up to 1 billion Swiss francs of cost. That's why understanding the mechanism and factors is crucial to mitigate the impacts. On top of that, due to climate change, the intensity and recurrence increase. Here is a Swiss map, and you can see the location of the landslide at the east of the Lehmann Lake. Few characteristics: the width of the landslide was around 30 meters for a length of 200 meters. The depth was between 1.5 to 2 meters, and the volume of the mass was around 4,000 cubic meters. Unfortunately, we didn't have any data of the saturation of the ground. Three apartment buildings were evacuated, and on top of that, significant damages to infrastructure and property were noticed, especially on the road you can see on the right picture. So for the last few years, we have recorded 4 landslides, one in 2018, one in 2020, the landslide in this study in 2021, and during this study, we also have recorded another landslide in 2023. This study employed a multidisciplinary approach. We started with a historical review. Then we performed a geotechnical investigation with sampling and lab analysis. This analysis was needed for the modeling, and we modeled different scenarios with GeoSlope software. The oldest picture we were able to find in a Swiss Federal Geoportal was taken in 1938. And at this time, we have noticed some sign of different landslide highlighted by the yellow arrow and the red circle. On the picture in 2004, we still have the trace highlighted by the yellow arrow, but the landslide inside the red circle was completely recovered by vegetation. And on the picture taken in 2020, we can see the 2018 and the 2020 landslide, and it was in the same area than the landslide occurred in 1938. So it's not just one landslide, it's a repetitive process. We have taken 6 samples on the slope of a landslide. This area was characterized by a weathered gypsum cover on the rocks, gypsum rocks. This table summarizes the value obtained in the lab test. So according to the USCS classification, we have mainly a silty sand on the ground. We also performed a triaxial test to get the value of the cohesion and the internal friction angle. We take the mean of this value for the modeling. So, like I said, we use GeoStudio/Slope software. We generate a cross-section of the median axis of a landslide in the 2021 landslide with the Swiss Federal Geoportal data. We change a few things to obtain the different scenarios. So we change the variation of the saturation of the ground to 0 to 100%. And we also change the variation of the thickness of the weathered gypsum layers from 1 meters to 2.5 meters. On top of that, we also add a load representing the forest load. These 2 tables summarizes the value obtained with GeoSlope software. It is the safety factors, so above 1 we are stable and below 1 we are unstable. We can say a few things. For a complete saturation of the soil, the slope is unstable at all in all cases. And for 50% of saturation, we are almost unstable in all cases. The decrease of the safety factor is higher when we increase the saturation of the ground than when we increase the thickness of the weathered gypsum layer. So the aim of this study was to study the evolution of the safety factor in function of the saturation and the thickness of the weathered gypsum layers in order to obtain the main factors influencing the stability of the slope. Unsurprisingly, saturation is the key factors, and then we have the weathered gypsum thickness. Forest load is a minor impact, just due to the load of the forest. With this value of the safety factors, we were able to draw 2 graphs, this one and this one, representing the value of the safety factors in function of the thickness and the saturation. So we get 8 linear equations. With this linear equation, we were able to calculate the critical saturation level for the 4 thickness to obtain a safety factor of 1. We get this value of level of saturations, and then we were able to draw a new graph. 2 curves representing a safety factor of 1 in function of the saturations and the thickness. These 2 equations, so below this curve, we are unstable. We trigger landslide with this condition, and above this curve, the slope remains stable. Now, we check with the data we get from the last 2 landslides. So the 2021 landslide, the estimated depth was between 1.5 to 2 meters. Unfortunately, we didn't know the saturation level of the ground, but we just know that heavy rains occurs few days before the landslide. For the 2023 landslide, we were more lucky because we put some humidity sensor on the slope to get the value, and the estimated depth was the same, so around 1.5 to 2 meters, and the saturation recorded was around 40%. And if we check on our curve, for 40% of saturation and an estimate between 1.5 to 2 meters, we are below the curve, so we are unstable. So it matches with our model. In this area, critical conditions correspond to a weather gypsum depth between 1.5 to 2 meters, combined with a saturation of the ground between 35% to 45%. In conclusion, gypsum saturation is a critical factor of the slope stability. Instability occurs at 35% to 45% saturation for a 1.5 to 2 meter depth altered gypsum layer depths. The 2023 landslide confirmed the accuracy of the numerical modeling. Forest overload is a minor influence on the slope stability, but the root-induced weathering increased the gypsum alteration thickness, so it has a long-term impact. Today, we just need to continue monitoring the area for an early warning and mitigate the risk on this slope. Thank you for your attention.
Yeah, if there are any questions, we can have a couple of questions. Yeah, very good presentation. Thank you. We will move on to the next presentation by A. Tarafdar on landslide susceptibility mapping of East Khasi Hills, Meghalaya using GIS-based logistic regression method. Yeah, please.
Good afternoon, everyone. So I'll be trying to wrap it up as early as possible. So this is almost the same method. Just the study area is of more importance because it is East Khasi Hills district of Meghalaya. As many of you will be knowing, this is the district that has the locations like Mawsynram and Cherrapunji. So those were the areas that receive most of the rainfall in India. So now, yeah, it's reducing, it's coming towards Maharashtra, but these are the areas that have had most rainfall. So the basic thing is the similar only. I'll just be going into the depths of some of the important parts here. So this is East Khasi. This is one area that had landslide just recently. This was a 7-story building, and the landslide happened just next to the building. This is an area called Maulai in East Khasi, just near to Shillong. So this is an area that our team had just taken into account, and like we had given some slope stability measures for this area. So that building will be demolished now. A new building, demolished for 3 floors will be demolished from there, and a new building will be constructed just next to it. So Meghalaya, like East Khasi Hills, it has 2 things there. It has very steep slopes and very high rainfall. So landslide is very common in that area. Almost every year, whenever in the months from June till September, there will be numerous landslides and loss, and very regrettably, there is loss of lives every year. So that is why we had taken this study area. Different methods have been used for Meghalaya, but just logistic regression for one major district was not done. So this is the purpose of this study. So Meghalaya has geological falls and all, steep slopes and high rainfall. So again, we had used GIS and for slope stability. So this is the map for East Khasi Hills district of area. This is the elevation that we had taken as the base for this area. So again, very high rainfall is there. The RL, the elevation is very high for these areas. It is bordered by Bangladesh to the south. There is a steep curve just at the bottom area. The bluish area, it has very less slope. So there is a steep curve from Cherrapunji. Cherrapunji is towards the southern of that part, south, Cherrapunji and Mawsynram. They are towards the southern reaches. So there is a steep curve, and that area is very susceptible to landslides. So this is again the same methodology we had used. We had done the analysis through ArcGIS to get the input data, then input models. Then we had used logistic regression to get the regression coefficients. We had done the AUC, ROC curve to see whether the model is giving sufficient value. So this is the basic outline again. So we had taken around 1600 landslide and non-landslide points. These points were taken from Bhukosh portal of Government of India. So those landslide points were taken here. So here, surprisingly, 11 factors came out as significant factors for this method. So when we had done those VIF preconditioning for Orissa, we had got only 7 factors. For East Khasias, these 11 factors, they were all giving good amount of VIF values here. So these are the factors that we have taken. That is the source of the data. Most of the data was derived from the DEM. Some data was derived from ISRO, NRSC, and Bhukosh from Government of India portals. So this is the same equation. We had used the same method, just 11 factors this time. So implementation was again done there on these. So the B factors, and also I'll just move into the conditioning factors. So elevation was there. So this is the elevation map. Slope map that was derived from elevation only. Elevation was derived from the digital elevation model. Here we had taken a DEM of higher resolution. We had taken the higher from the Alos Pulsar dam that is having 12.5 meter resolution. So this was used for this one. This is the aspect again, profile curvature. We moved the rainfall data. So rainfall we are getting around 4,700. We had taken it as the average from 2011 to 20. There's one website known as CRUTS. So from there we had derived this data. So that data was taken out from here. And this is the average actually in Meghalaya. We are having more than 7,000 mm or sometimes more than 11,000 mm of rainfall over the entire year in Cherrapunji, Mawsyngram, those areas. That is the lithology map. From Bhukosh, it is downloaded very easily. This is the distance from river again. Drainage density is just the number of drainage in a particular region. Drainage density was giving significant values here. Distance from road again, LULC again. In LULC, those red areas are the built-up areas, the town areas where most of the like forests had been cut. People are mostly staying in those red areas. Green areas are the forestry areas. So we had stream power index. These are all derived from the DEM. So this is the final result that we got here. That is the landslide susceptibility map of Meghalaya. These results are depending on the district. In that given district only, the areas having green values here, those have low probability of having landslide. One with red and orange are one having very higher probability. Still, even those areas having green results, even they are having good landslide probabilities because this we had done only for our district. When the same study will be done for the entire state of Meghalaya, that green, because it's relative probability, so that green areas will also be coming into moderate and like that. So for very low is like around 86%, the rest of the part is high. And very surprisingly, most of these areas, even near our campus, they are in sites of Ensora. Some of the landslides had happened in the previous 2-3 years. So we got those values also. So this is the AUC ROC curve that we did for verification at the end. We got a AUC value of 0.9. So from studies and all, a 0.9 value is very acceptable here. Interesting part, 8.5%, we saw it. Those areas that are having 8.5% area are mostly near steep slopes and near the road networks. So, and here, like in Orissa, we had LULC as one of the most crucial factors. Here, slope and distance from road were the crucial factors. Slope was the most crucial factor, so those areas that are having very high slope are mostly susceptible to landslide. Again, distance from road was coming here also. So, and then we had divided into 4 zones here. And so I'll just be trying to. So these are some future studies that we are doing, and I'd like everyone to try this because like to do this other machine learning methods. Nowadays encapsulated methods are being used like anything. So we also want to do this, do with other methods and then check the results. So that is one future scope. Temporal analysis we could not do due to lack of time. So for different periods of time, this can be done, and some additional conditioning factors. We had taken 19 conditioning factors, from there scrapped out 8 because they weren't giving good results. Then from those 11 conditioning factors, we got these results. But due to lack of data, so some other factors from different papers might also be taken into this paper. So these are some of the references here. I'd really like to thank Government of India for the past 5-6 years. Getting data has become very easy. Before that, getting GIS data was really difficult for us. So these are the references. Again, I'd like to thank my committee member, my group members, and Geotech Asia once more for giving me this podium. I'd like to thank you.
Yeah, good presentation. Any questions? Yeah, I have a query. Actually, what is the resolution of the DEM that you have used?
Sir, 12.5 meter in this study.
Okay.
12.5 meter into 12.5 meter. Sir, that is Elos pulsar DEM. And the previous study, sir, we had used 30 meter into 30 meter. So that was ester DEM, sir.
Yeah, fine. But that is something that you have to look at actually, because when you are considering a very small region,
Yes, sir.
okay, you may have to use higher resolution
Yes,
DEMs.
sir, getting data was the difficult part. So, sir, we have Cartosat DEM of ISRO. That is 10 meter resolution. But, sir, we have to purchase that DEM. So,
Yes, yes.
freely available, so we could only get.
And how geotechnical aspects are considered in your study?
Sir, geotechnical aspects sir, we have taken slope, lithology is being taken
Yeah,
into account,
yeah.
sir. So,
That is based on your satellite data or your LUSC lithology map.
Yes.
But actual site conditions, any soil sampling for.
no, sir, we haven't taken because it was a bigger area. But, sir,
Yeah.
we are doing, sir, one such, we had one project, sir, a bridge construction site was being done. Sir, there we are trying to take satellite data also. And, sir, soil we had, there the borehole testing and all, get the lab data. So, we are still working on that, sir.
Okay, thank you. Yeah, take care. So we will move on to the next presentation on high strength steel mesh modules as a rational and sustainable coastal protection solution by J. Mukheja.
Good afternoon, everyone. Thank you, Geotech Asia, for this wonderful opportunity to present the solutions. I'm representing a company, GeoGroup. It's a Swiss-based company, and it's a 75-year-old company which is focusing on all the solutions made out of high tensile steel, and which are actually applied against natural hazards, and mainly rockfall instability, slope instability, shallow landslides, avalanche prevention systems. And now this is a very new addition, which is called the high tensile steel mesh, which is focusing mainly on the problems for coastal erosions. And because India has a very big coast, and we also come to know about a lot of problems, people approach us, and it's not just about the coast, it's not just about the sea coast that we have, it's also about the erosion at river levels. Different tributaries in different states have got different issues, and scouring is one problem, as we have seen in the recent calamities as well, that scouring has led to a lot of problems, causing damage to villages, encroachments, hill cutting at the bottom level, at the toe level, and also disturbing the road alignments. So this is one thing that we wanted to discuss here. So I'll just quickly run by the introduction. This is one thing. This is a study by UKCP. UKCP is the climate projection study, and as you can see, it is comparing 3 different models where the carbon emissions and the carbon dioxide, if it's in the peak and decline, or if it's stabilized by 2100 century, or if it's completely it's not under control. So they are predicting that the sea level is expected to rise between anything between zero point 0.2 to 1 meter by 2100 century, and depending upon the emission scenario. So, some scientists believe that these are very safe figures. These are very, conservative figures considering uncertainties in the behavior. So, why is it important to study this sea level rise? It is important because then, as you can also see, there are a lot of studies around the Mumbai area and the Mumbai city that most part of the city would be submerged or something like that, and the sea level rise would be there. There's a threat to the cities. So it's also important to understand the phenomena, how it happens, why it happens, what impact it can have. So the major impacts that are contributing to such damages, that's scouring, displacement, impact forces. So all of that has to be studied, and we have done a lot of modeling to understand the current situation, the future projection, and what it could have an impact, what kind of an impact it could have in the future. So this is again future global coastal erosion scenario under different conditions of emission. This is a brief portfolio of the systems that we produce and design. So here majorly we are going to be focusing on the coastal erosion measures. So this is a video demonstrating the application, and you can see around on the coast, the system made of high tensile steel is installed over there against the impact. Now there are a lot of factors to consider, and we have to see a comparison of the conventional systems versus this side of an approach, and if there are any findings, if there are any positive findings which are having impact on the nature, on the impact forces, on the scouring or the run-up of the waves, and also what is the sustainability, what is the addition to the sustainability. So now we know as the gray method, we have just categorized it in such a way that the gray methods are full structural methods, hybrid methods, and the green or ecological methods. So we have got breakwater approach, we have got the rock armors, we have got obviously the concrete solutions. Then we have got rock armors with vegetation, natural sea wall with salt marsh, and we have got the shore nourishment approach or vegetation. But there are some different pros and cons of both type of approaches. Of course, that can be seen that it's a long-term solution when we talk about the gray methods. But on the negative side, they are much more expensive if you want to treat the entire shoreline or a coastline or a river area. Then it's also causing a lot of high emission. So idea is we want to study the rise in the sea level against climate change, against emissions. Now what we are proposing as a solution is very contradictory. It is also a contributor to high emissions, which we think that this is the major culprit to the climate change, which is anyway bringing the temperature up, global temperature up, and also causing the sea level to rise. So we have to see the solutions which are in the long term sustainable, at the same time technically suitable. So it has to be a balance between the requirement of protecting the line, plus also in the long run, in hundreds and 200 years to come, should not contribute to that very factor, which is, again, the main reason for the kind of a problem. Then, if you compare this kind of a cell, which we call as the techo cell, it's made of high tensile steel. What it does is it, traps a lot of rocks, small boulders, big boulders, and then we try to make a solution out of it based on the laboratories modeling, and the findings are that it's reasonable cost-wise. It's very effective in both in terms of technical and financial suitability, and emissions are minimum, and it is also proven very fruitful against, very efficient against the powerful waves. So Just a brief comparison of the solutions that are available today, which is one of them is the rock armor. So one thing is that it's very high in emission, which is again a problem. Then the wave energy dissipation is on the lower side. We'll have a video from the lab. Then it shows clearly how the energy is dissipated. So it's easier to understand the dissipation part. Then there's a risk of overtoppling and flooding. And the overall conclusion is that the erosion control is not that optimum. Then we have got the tetrapods, which is again a very, very generational old thing. We know about the system. We've seen it in Mumbai as well. And again, the same factors are there, which are high emission and low wave energy dissipation. Again, we have got the concrete slabs, which is also a very popular approach, but we cannot ignore the fact that they are very high in emissions and the maintenance cost is too high. Although wave energy dissipation is good, but one of the other factors related to sustainability is something that we have to consider. Then again, this is the Gabian effectiveness, where we have seen that the buckling and the sliding are one thing which are causing the displacement and which is not holding good in the long run. Then the concept of this kind of a cell.
Please try to conclude in about 2 minutes. Okay.
Yeah. Okay. So the concept of this approach, TechoCell approach, it's very flexible in nature. The flexibility allows the energy dissipation to be uniform, and it helps in reducing the run-up of the wave. So I'll just quickly skip this and come to the videos where you can see. It's a laboratory investigation where you can see a lot of trials were done just to see how the wave impacting the solution, it dissipates. And you can also see the displacement in this case, or you can also see the run-up. As when we just compared all these things in the laboratories, then we see we compared for both type of trials, the solitary waves and consistent waves, and the run-up was also measured. So if you see in the last column, the run-up is measured in millimeters, which is the lowest in the case of TechoCell and rock armor. As you can see in the second video of rock armor, the splash, the energy dissipation and the splash is a bit inconsistent, which also shows that TechoCell shows better wave absorption and less wave dispersion and splashing, which also helps in reducing the scouring. Next factor is that we can use the aggregate with small stone size. Also, because of the high flexibility of this mesh type, it is much more suitable to have that to incorporate and accommodate this at different angles. So this is a brief comparison of the TechoCell showing 50% reduction in the wave run-up, which is one of the most key factor in learning about the application of such systems and their success and effectiveness. This is probably the last video that I would like to show, that a wave was generated to see the run-up.
Yeah, please conclude. Time up. Yeah.
Okay, thank you, sir. So with this, this is majorly about the application of this system across the coastline, across the banks where we see a lot of problem, where we see the problems of the waves hitting. Every year there's a problem of more and more land getting encroached with the waves and getting sacrificed. So this is just an attempt to compare different type of solutions and how we must address this for the next years and decades to come, and find a more sustainable and green solution. Unfortunately, we had a lot to discuss, and unfortunately, my colleagues could not join here, who are also the co-authors here, Mr. Christoph Balg and Mr. Roberto. So they were also supposed to come and do the presentation, but unfortunately, due to some bad health, he could not come. But thank you, the members, and thank you this conference for hosting. And obviously, this is a wonderful event. And in my 15 years, I've not seen such a platform where we could see so many participants coming from abroad and India, and also doing such great presentations. Thank you once again.
Thank you, Mr. Mukeja.
Thank you.
For your presentation. It was a nice presentation, but I could
I
understand you had
fully
a
understand.
short time for this.
Yeah, fully
Hope for
understand.
the next session once
Definitely,
again.
definitely. Thank you so much.
Any quick question? One question from the audience. It was an interesting laboratory investigations and all which you are showing, including the modeling. Yeah.
But I'll be available if anybody has any question. We can also entertain it.
Yeah,
later.
he can be interacted. Thank you.
Sure.
Thank you, Mr.
Thank you so
Mukeja.
much. Thank you.
So we'll go for the next author, Mr. Shashikant, on the topic parametric study on MICP and enhanced slope stability through numerical modeling. Mr. Shashikant, yeah. You have 8 minutes, okay?
Good afternoon, everyone. First of all, I'd like to thank Geotech Asia for giving me this opportunity to present my work in front of you all. I'm Shashikant, and I'm currently pursuing my PhD under the supervision of Dr. Rahina from IIT Ropar. So today in this presentation, I will present my work on parametric study on MICP enhanced slope stability through numerical modeling. I will cover these content. So this is a basic introduction about the landslide we already know. Landslides are the movement of rock, earth, or debris down a slope due to gravity. It always requires triggering mechanism for landslide to occur that can be natural, anthropogenic, rainfall, earthquake, volcanic eruption, nearby explosion, etc. So in this work, I have focused on rainfall-induced landslides. Rainfall-induced landslides are triggered by heavy or prolonged rainfall. It has both global and local level impact here. Globally, more than 30,000 landslides occur because of rainfall. It causes 3,000 plus death, 12 billion economic losses every year. In India also, 12.6% of the land is prone to landslide, and 3,300 landslides occur every year. If we talk about rainfall-induced landslides, these are often shallow in nature, and depth is usually less than 3 meters and parallel to the surface. So there are many landslide mitigation strategies that are there, including the precautionary measures that can be taken. So there are some direct method of preventions also and indirect method of prevention also. So direct method of preventions includes modifying the soil slope, reinforcing the slope. Bioengineering can also be done. But there are some constraints on the conventional technique that usually includes a high cost or limited availability of the material, potential ecological disruption, and it is sometimes very much difficult to apply some of the solution in difficult or complex terrain. So in this presentation, I will focus on bioengineering part, basically on MICP. So MICP is a microbial-induced calcite precipitation in which ureolytic bacteria excretes urease enzyme, and because of this urease enzyme, urea get converted into carbamic acid first, then that get converted into carbon dioxide and ammonia. That carbon dioxide, again, that is dissolved in nature, so it will get converted into carbonates and bicarbonates. These carbonates, in presence of calcium ion, get converted into calcium carbonate, and that calcium carbonate actually helps in bonding the soil particles, and it fills the soil pores. This is the basic overview of the work which I've done. So first we have an untreated slope. So what happens when rainfall occurs? Fast infiltration happens. Due to that, there's an increase in water table, there's an increase in pore pressure, and because of that increase in pore pressure, saturated soil usually loses strength and slope failure occurs. Also, erosion is one of a major issue because of rainfall. So if we are doing that surface treatment on the slope using the MICP technique, or EICP also can be done. So urea solution and cementitious solution can be provided on the surface. Treating the surface will basically reduce the permeability of the topsoil. Also, it will strengthen the soil. So the infiltration can be delayed, and because of that, slope failures can be reduced. So a numerical modeling based on this idea has been done. So basic geometry was made in which water table was considered by using the total water head at 8 meter from left and 6 meter on the right. So total 3 different slope angles were taken here. 30 degree, 45 degree, and 60 degree, and analysis has been done on 5 different rainfall conditions for 24 hours, that is 20 mm per hour, 40 mm per hour, 60 mm per hour, 80 mm per hour, and 100 mm per hour. The mesh was generated at 0.25 meter global element size. These are the hydraulic properties which were used in the studies that has been taken from the literature. The Van Ganichen parameters are shown here. Van Ganichen parameter were used for the unsaturated soil here, and for untreated soil also it has been taken from the literature. The hydraulic conductivity for saturated soil, for untreated and treated soil is also shown. So these formulas were used for the numerical modeling. These are the shear strength parameter which were used for the untreated and the biotreated soil. The average was taken from different authors' papers, and mostly these have been done on the sandy soil. So this is a general slope stability analysis results that has been done after the transient seepage analysis. The last time pore pressure readings were directly given to the slope stability analysis on GeoStudio Slope W. And it can be seen that if after the surface treatment, even at higher rainfall intensity, it is safe, and factor of safety get increased because of the treatment. So these are the conclusion of the study that that includes that factor of safety improved from failure to safe for gentle and moderate slopes, but for steep slope for 60 degree it was still vulnerable for higher intensity rainfall. So there's a need of still more reinforcement can be done. Also, MICP treatment can be done multiple times to increase, or a new parametric study can be done to check how much depth is required for better stability of the slope. So there are some limitations also for this study. It's a small work that includes that average soil properties were taken, and there special heterogeneity of MICP was ignored. 1 meter, the top 1 meter was taken as the MICP treated soil. Also long-term durability of MICP is still required to be done, and field scale validation is required. So I'm working on that. These are the differences. Thank you so much.
Any questions from the audience? Yeah, good work, good presentation. So we will move on to the next presentation. This one. Yeah, on-shored reinforced soil structure for enhancing accessibility and infrastructure at Tara Tarani Temple by Ratnakar Ramesh Mahajan.
Very good afternoon to all of you. I am going to talk about the basically shored reinforced soil hybrid structure The photograph what you see on the right is one of the Shakti Peeth, Taratarini, and I am happy one of my ex-colleague Chiradev is attending this presentation, who was part of this great project we did. So this project actually required some improvements, as there are a lot of pilgrims visit this temple being a Shakti Peeth, where it was required to widen the road and create a platform, because there are a lot of people visiting, so parking space to be created, and this temple is on a hilltop. Now, being a hilltop, and if you want to create a flat land, it requires very steep structures to be built. This is the plan from, let's say, the satellite imagery. The red dot what you see is a temple, and that's the left portion, the rectangular area where support was needed, and then a parking area to be built. So presently, if you see, the road is going in a bends, and then the people are reaching at the top near the temple. So conventionally, any reinforced soil structure you build, you require, as a rule of thumb, reinforcement which is around 70% of height. So if it is 10-meter high wall, you require around 7 meter of the reinforcement length. But being a hilly area, that was not possible to provide such a long reinforcement. You will see the requirement. So here, reduced reinforcement length, that was what was required. So in this project, looking at the complexity and the, let's say, the heights, what you will see in this picture, to make it simpler, I put it on the constructed structures. The bottom tier is around 27 meter high. This 27 meter high structure is, you can see, completely in one go it's going. Then a flat land is created, then 7.5 meter, and then another 30 meter that is to be built. This whole area was required to be built considering the whatever existing soil property. So if we just, for the sake of understanding, club all that together, it becomes 62 meter high structure, 62 meter high structure of a reinforced soil structure. Here we use the 2D limit equilibrium analysis. The software what we used provides an approach of predicting the lowest factor of safety of given soil parameters. And in this project, we use both approach, that is the circular slip surface as well as non-circular. The reason being, some portion of the hill was there, which is, let's say, a mix of rock, and then we are going to fill with the soil. For load combinations, we have used the dead load of around 30 kPa, which is very minuscule compared to the vertical load, and the horizontal seismic accelerations of 0.05 based on the seismic zone. For the design of this structure, the Indian Road Congress IRC SP102 as well as IRC 116 that's being utilized. For designing these complex structures, usually you cannot either BS 8006 or other, because there is no definition or the guidelines for design of the hybrid structure, where that's why we have used the FHWA. In this project, we have used a geogrid of strength of up to 600 kilonewton per meter, and as a part of nails, soil nails were used. Also, the pre-stress anchors were used. So, bottom of the structure, the pre-stress anchors are being used with a capacity of close to 1094 kilonewton, and for the soil nailing is 230 kilonewton capacity nails were used. For the design point of view, the static factor of safety was required to be achieved as 1.3. So being 62 meter tall structure, it was very challenging. However, with the help of pre-stress anchors, we could achieve this required factor of safety of 1.3, and seismic shall be more than 1.1. While doing the analysis, we have checked for bearing capacity, the pull-out, tension failure, as well as the sliding and overturning. Very important part for such a tall structure is the drainage, because it's a lot of water is expected to infiltrate. So here, drainage composites are being used at the back of the reinforced soil structure, as well as the non-woven geodexil has been used as a filtration material behind the fascia, that's behind the terra mesh. As a part of the construction sequence, first the soil nailing was done, so excavated surface soil nailing, followed by the geogrid installation, followed by the gabion or let's say terra mesh construction, and then the anchor installation. The anchors were installed and they were checked for the capacity by doing the pull-out test. So overall, it's the aim what was required to build up a 32 meter of additional space that is achieved with additional 30 meter hilltop extension and overall retention of around 62 meters. The advantage of this system is being a flexible, even there are some movements, it will be accommodating that. Additional parking space provided to the pilgrims, of course, attracts even more visitors because it will be a nice experience, as well as this is an environmental friendly structure compared to the conventional concrete structures. In this, the connection of the high strength geogrid with the nails was done by using the steel wire ropes wrapping around the geogrid outfit, and that makes a unique project for such a complex conditions. Here, I think for such structures it is required to monitor the performance of let's say for further few years to establish how these structures can be further incorporated in a practice. Presently, these kind of structures are not very common in India. It's now getting further. Would like to really acknowledge the efforts of the technical team which has put up, because it was a really complex project for us, as well as support from the IIT Bhubaneswar, which was involved in reviewing the designs, as well as the department itself, which was very keen to take this project forward. Thank you very much, and would be more than happy to answer any questions.
Yeah, very good presentation. Are there any questions from the audience? Yeah, please.
A very challenging venture. Congratulations to you. Nice presentation and a case study. My doubt is, what is the loading we have considered? It is for the parking area. We are trying to widen the base, correct? Yeah. And any trucks also that loading is taken into account? And if so, what is the distance from the edge the vehicles are to be placed? Is that any specifications?
Thank you, sir, for your interesting question. Yeah, the part of the loading, of course, some portion is for the road, so it's a live traffic load is being considered. However, for the parking space, it's mostly the pilgrims visit, which is typically the cars or the bus, but not really the heavy trucks, because it's a temple, so even not much of construction activity. So heavy loading is not considered, which is light loading in the tune of 30 kPa that's being considered. As far as the distance, actually we have, while designing, we consider throughout the cross section, that is from fascia backside. However, from safety point of view, behind the fascia around 1 meter, usually the traffic barriers or let's say safety barriers are usually installed, and it will be advisable from safety point of view also to be parked little away from the fascia.
So equivalent surcharge had been taken to cater to the...
Yeah, roughly 1.2 meter
and when you started from the base,
yeah,
you had to do some cutting of the existing.
Correct.
So during that time,
yes,
the stability was checked?
Yes, so as a part of design, cut slope was first analyzed once we cut it for the excavation, whether it is stable or not, and then accordingly we provided two nails here, two types of anchoring. One is the soil nails and one is the pre-stress anchors. So pre-stress anchors were provided to take care of the overall slope stability, including the cut surface. And the small anchors were being provided to take care of the compensate the short available space for the geogrids.
One more question. Was the backfill imported or it was locally procured?
It was local available material, and the beauty of this, like I think this is the first time I'm getting this question, the beauty of this system with the flexible fascia, you can accommodate little bit materials with fines. So typically for infosoil, 75 micron passing usually restricted to 15%, but being a flexible fascia, even you can go up to 25% easily. And that's what we have been practicing, little different than the industry. Thank you.
Excellent. Excellent contribution. Thank you.
Thank you. Thank you very much. Thank you, sir.
Yeah, I have a query. So which year this was completed?
Maybe Chiradeep, can you help me?
2022 it was the
2000?
final, yeah.
22.
22, yeah.
So are you monitoring the performance, whether is there any deformation or displacement?
We have actually suggested to do that, but overall, visually, what's being seen, it's good.
Yeah,
But
because
not being monitored.
No,
till
in
now.
Mangalore airport, no?
Yeah.
It is now more than 5 years. Similar construction, it is about, I think, close to more than 50-meter high. But their deformation was not visually observable, but some collapse happened last year.
Yeah,
So it would be better to monitor.
Sure.
Yeah. Okay.
Definitely.
No, the local contractor who has actually built that, because of the department's pressure and his DLP period, so it is being monitored by them and regularly, get in touch with the company, with Makafiri people.
Very good.
Thank you.
Thank
Thank
you.
you, sir.
Thank you. So in this parallel session on slope stability and landslides, yeah, it has been a wonderful session with a lot of excellent presentations. We had a good mix of topics starting from landslides, susceptibility mapping, to slope stabilization using laboratory methods, then field techniques, even coastal protection, as well as practical field case studies as well. So we thank both of us, both myself and Engineer Chakravarti sir, we thank all the presenters for making excellent presentation and completing on time. Also thanks to each one of you who are present here in the fourth day, last day of the conference. All of you are here with complete attentiveness. So thank you for being here with us for this technical session. And we are on time. Yeah, this was scheduled up to 3:30. So team speaker, however, could not be present here. So thank you all once again, and I will hand over to Chakravarti sir for any final remarks, if any.
It was a wonderful session, though we have missed the theme speaker, engineer Taro Hiromana, for maybe the reasons beyond his control. So we had a good variety of presentations, including the case studies and the lab studies, which we've been also looking at the slides and the presentations they are making. So once again, thank you one and all, and thank you the organizing committee for giving us this chance to chair and co-chair the session. Thank you all.
I thank the chair and co-chair for handing over the today's session. Thank you, sir. Since we are at the end of today's session, I request chair and co-chair to permit the coordinator to close today's contribution presentations. Permitted. I thank today's chair, Dr. Srivalsa Kolatiyar, and co-chair, Engineer AVS Chakravarti, for accepting and leading the today's session. We have a guest for this session, Dr. Sunil S. Basakar. We have a few lines for him. Dr. Sunil S. Basakar has industry experience of more than 20 years and 16 years association with academia in the field of foundations and geotechnical engineering. As a field professional, actively involved in geotechnical and foundation initiatives, including ground improvement and strengthening works for mega infrastructural projects. He has spearheaded introduction of CFA piling technology in India. He is member of ISSMGE and fellow of several professional organizations like the Institution of Engineers India, Indian Geotechnical Society, and serves as editor board member of DFI Journal USA. I thank you, sir, for as a guest for today's session. He is also the educator who educates the educators. So I request the guest, Dr. Sunil S. Basakar, to present the mementos for today's chair and co-chair on behalf of Geotech Asia 2025. Thank you, sir. I request the chair and co-chair to approve and permit me to end the today's session officially. Permitted with the approval from chair and co-chair, the today's session ends here. Thank you. I request all the delegates for a group photo session. Please come to the dais.
Yeah, let's have a quick round of a group photograph over here for this session. All of you are requested to assemble near the dais.